Afraid there'll be no music. Didn't get that set up in time. So let's move on to other waves other than sound waves. Let me try with my PowerPoint, see if that works today. Okay, well, we hopefully, how are you? Good. We hopefully have recovered from the midterm, and apparently not everybody has. But anyhow, today I wanted to move on to more study of the. I have to tee up something important. I wanted to do the study of wave mechanics in some detail. I have to get onto the air bears. Okay. There's this very nice website, I think I mentioned it before, that was put together by French people in Polytechnique. Hope we can call it up. Now, I'm hoping that you're reading the chapters. I can't go over every detail that's in the that's in the book, but what I'm hoping to give you is a generalized view of what wave mechanics is about, an overall view. Now, this very first demonstration from this PowerPoint, from this animation, shows. This is from this Polytechnique quantum physics thing. What they are doing here, they have 4 slits, and they're having both either waves of electrons, that is, electrons coming through the slits, or electromagnetic waves. What they're trying to show is that when the wave travels through 4 slits, it diffracts, whether it be an electron or a wave or an electromagnetic wave. But when it arrives at the screen, it arrives and creates one spot, which we knew actually in the old photographic film. When light arrived at the film, it would strike a small grain of silver iodide and convert the silver iodide to silver. And that's how you would get a photograph. So the wave did not illuminate the whole film at once. It illuminated one grain at a time, which should have been a clue that the light somehow, though it's a wave, it's not actually uniformly arriving at a place. It's arriving at a point. And that's what this animation is trying to show. Namely, let me start it again. If you start out with just a few particles, they travel through the slits, but when they arrive as points. Again, this is the mantra I've been preaching here for a few weeks now. Float like a butterfly through the slits, but arrive like a bee at one point, and you'll notice that in some places they don't arrive at all. So that gives you your diffraction pattern, which is built up one quantum at a time. So that's the general idea of the dual nature of matter and waves. There's a wave function which says that the wave is spread out. On the other hand, when it arrives someplace, it arrives as a quantum delivering its full energy given by h times f. And as Einstein said, light apparently starts out as a quantum. It's emitted by some oscillator, starts out as a quantum, travels as a wave, can interfere, diffract. So what you'll get, you see, if you have a diffraction pattern, is you'll have part of the wave traveling through one thing with some sign kx, kr, and another part of the wave may split. Just like an electromagnetic wave, the electric field will split, passing through one slit, passing through another slit. When it arrives at a certain place, you add up the two waves, and because there may be a phase difference, k being 2 pi over lambda, because there's a phase difference, where you have one traveled one distance, the other travels a slightly different distance, r2, because of the phase difference between them, when you add these two waves, but then you square it, and so you get this term squared and that term squared, but you'll get a term sine kr1, sine kr2, which will reflect the interference of the two waves. So the point is that just as with light, we got used to the idea that there is a field, and the energy in the field is its square. And if you have two fields, you add the two together, you add the two intensities, the two electric fields, and then you square it to get the energy in that field. And the energy can show interference effects because the two fields may be slightly out of step. The same thing will be true in quantum mechanics. We will have a probability amplitude, just as there's an electric field amplitude, psi1, and we can add it to psi2, and to get the probability of a particle being there, we square it. And you can get interference effects between psi1 and psi2. So you can have psi1 passing, you have some psi coming in, it splits as a wave will into two parts, one part passing through one slit, the other passing through the other. They travel different distances, and you'll get a difference in path between the two parts of the wave, and they give you an interference effect at the arrival point. And the amplitude will depend on the square of the sum. So that is, in general, is the story of how waves behave. But the tricky part is that when it arrives as a full quantum of that energy and causes a single spot on the arrival screen. So that's one general principle that, yes, someone?
Why do we square the professor?
Why do we square? Well, the thing that you observe is the energy. Okay. You don't actually observe an electric field directly. So we got used to the idea that the energy density, for example, in the electric field was E squared over epsilon naught. I think we wrote that. We wrote that the energy density in a magnetic field is equal to B squared mu. So we always square the field. We had in a capacitor, for example, the energy in a capacitor was always something like a V squared over, I think it was maybe CV squared or something like that. It's always the field squared. It turns out what the energy is. So this should be a fairly familiar idea from what we've dealt with fields before. So what you want to think of is that psi is kind of like effectively a field, and the energy in it is the square. We actually interpret this as a probability density, the probability that the particle, if it's a particle, mass particle, that the particle is in this is per unit in this volume. So you multiply this by a volume, and you'll get the probability that the particle is there. Let's go on to look at a couple of cute things from this nice application. This this is another fundamental idea of this particular the subject being that de Broglie's idea that a material particle having a momentum p, usually the momentum is given by mv, but de Broglie said associated with that momentum of a material particle should be a wavelength, h over lambda. Lambda is the wavelength of this particle. So what this is saying is that the faster the particle is going, the smaller is lambda. Now that idea, if you remember that, you can solve an awful lot of problems. Now it's illustrated in this particular demo. This line here is the energy. Now, if I lower the energy, you'll see the wavelength getting longer. So this is supposedly the wavelength of a material particle, and it changes with its energy. If I make the energy higher, 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 the wavelength gets shorter, shorter, shorter. So it's as though it has each wave crest gives you a punch, if you want to think of it that way. So the higher the energy, the more punches you get per second. You could maybe think of it that way. However you remember it, this is the key idea. And the point is that you keep getting, just remember that idea, that as the energy, kinetic energy, gets higher, the wavelength gets shorter. And as the kinetic energy gets lower, because the kinetic energy, I should make sure you know, remember this point, the kinetic energy was given by a half mv squared. Now mv is the momentum, so I can, if I multiply this by m on the top and m on the bottom, I haven't changed anything, but you see this is mv squared is p squared, so and I have 2m over here, and p is given by h over lambda over here, so I get h squared over 2m lambda squared. So this is an expression for the kinetic energy of a free particle. The kinetic energy goes inversely as the square of the wavelength. So I think that's what that animation is showing. As I lowered the kinetic energy, the wavelength gets longer. When Ke goes down, lambda gets larger, and as my kinetic energy goes up, lambda gets shorter. Okay? Very important idea. And it fits in, let's see what we have here. Okay. It fits into one of your homework problems. We were working on that in my office hour, where we were fitting a wavelength into a box, and the first wave, you fit. The idea is that these quantum mechanical problems, to find the energy states, what you have to have is a certain confined space, and what you're trying to do is fit a wavelength into that space. This is very much like the Chladni modes that I showed you the demonstration. At low frequencies, you get certain modes. As that frequency goes up, the wavelength gets shorter, and you get more modes and various fancy shapes. Same thing is true here. Here you have a low frequency, long wavelength mode. and it fits into the box. It fits in the sense that these are supposedly infinite walls, so the particle can't get out. It can't get out at all. So it has to be zero at the walls, because that tells you inside the wall it's zero. But the next level is a higher energy. In other words, the ball is bouncing back and forth at a certain speed. At the next level, we represented, again, it must go to zero at the boundary. So it looks something like that. So you get two half wavelengths. This is a higher energy. It's a higher kinetic energy because the wavelength there is shorter. The wavelength here is equal to the length of the box. The wavelength here is equal to half the length of the box. And we get yet a higher energy up here where the wavelength is yet three half wavelengths is equal to the length of the box. And just by this simple thinking, as the wavelength gets shorter, the kinetic energy is getting larger. By this, inversely, as the square of that wavelength. So that's that idea. Now, the other idea that you want to grasp is that if the kinetic energy, that's this line here, is, well, okay, let's do what we did before, namely just lower the kinetic energy, which will make the wavelength get longer or shorter. If I lower this. You bump into it less often, and the wavelength gets longer as you lower here. Low energy. Okay? Now, as I raise the energy, it does what I did before on the right side of the picture. Okay? Now let's consider here is a step. Think of this as the ball rolling against a wall that has a certain height. So now let's go to the limit where the ball has enough energy to get up over that height. This is kind of a potential energy. It's like rolling up a hill. Now, if I give enough kinetic energy, I can roll over the hill. But you'll notice here, before I roll over the hill, the wave dies out. It does live a little bit into the hill in this case. I'll explain that in a moment. But if you have enough kinetic energy to ride over the hill, you would think it would become a wave again. See, if I go over the hill, it's a wave, but all the kinetic energy that it has is from here to here. Again, this is the conservation of energy. The total energy is this much. I've ridden up the hill and slowed down, so from here on out, it's a slower moving ball, and because it's slower moving, its wavelength is longer. That's a very it should be reasonable. It's unfamiliar, but reasonable, okay? Do you get that? Is that clear enough? I see some blank looks. You get this idea that if the particle can roll up over the hill, it's going slower. In other words, if I'm a particle and I'm rolling and I'm going up the hill, granted I had here a steep wall, but let's make the wall a little slopey. If I ride up the hill, if I give it enough kinetic energy, well, if I give it too little kinetic energy, when it reaches this much, see, the total energy is equal to the kinetic energy plus the potential energy. And this is the potential energy, this curve here. So if I give it a certain amount of kinetic energy, it rides up until the potential energy is equal to the total energy. The kinetic energy at this point would be zero if I only gave it this much kinetic energy. However, if I give it this much kinetic energy, in other words, I roll it much faster, it rolls up the hill, and it still has a little bit of kinetic energy left because it's transferred a lot of potential energy here. Does that make sense? It should be actually have a nice physical feeling. Is it okay, more or less? Okay. So in quantum terms, because the kinetic energy is high, the wavelength is short. over here. But once it starts rolling up the hill, it slows down. As it rides up the hill, slows down even more, gets longer and longer. Finally, when it gets here, it's got some kinetic energy, but not too much. So here's a graphical way, a pictorial way of solving a quantum mechanical problem. This could be done mathematically and in more advanced. If we were interested in the math, we could do it, probably. But the idea is that up here, the net kinetic energy is only this much, and so the wavelength has to correspond to that much kinetic energy, and it will be much longer because the residual kinetic energy is less. Hopefully that makes some sense. Now, the thing that's a little bit problematic in this picture is what happens when your energy, kinetic energy, is not enough to get over the hill. Now, the peculiar phenomenon of waves is that the wave can actually propagate to some degree into the wall, into this potential barrier. That is something classically does not happen. This is a peculiarly wave phenomenon and doesn't happen with ordinary particles. But the analogy I have is like if you have some kids who are throwing a ball against the wall, if you don't throw the ball too hard, the ball will bounce back right off the wall. So that's classical. The ball hits the wall, doesn't go in through the wall to any extent, and bounces back. On the other hand, the noise of the wall, the sound, can penetrate through the wall. So if you have a wave phenomenon, the wave phenomenon can go where the particles can't go. That's maybe a pictorial way of thinking of this. If the wall is not too impenetrable, if the wall is infinitely impenetrable, like this one in your homework problem, there the wave does not enter the wall. But if the wall is partially penetrable, and as it is in this case, you see the wall is not infinite here. You'll notice, for example, so it does penetrate to some degree. If I make the wall taller, which I think I can here, that penetration should actually decrease because the wall is harder to penetrate. So let me see if that actually they do that for me without moving. Hopefully, it should actually decrease faster. Let's see. Let me try to bring it back down. I was going toward infinity. No, I don't want to. So as I get closer to getting over the wall, it penetrates further and further, hopefully, if the thing is right. And as I get to where the wall is, the kinetic energy is able to get over the wall, the penetration gets very large. And finally, when the kinetic energy is greater than thing, it actually can propagate as a wave beyond the wall. Does that make sense to you? Yes, Alan.
At what angle does it penetrate?
I'm not talking so much about angle. This is more or less in one direction. I'm thinking of, unfortunately, they have the wall as this way. I'm trying to think of it this way, so that it's riding up the wall. Even if it were a wall like this, if it rode up the wall, if I didn't have enough energy to get to the top, what it would do would ride up the wall, would stop. That's known as the classical turning point, where you've given up all your kinetic energy and you've got potential energy. It's like just rolling a ball up a hill. You can go a part of the way if you don't put up enough speed, and then it'll simply roll back. Classically, it will stop at a certain point called the classical turning point. I think that word is used in your book. Waves, though, they'll go up to the classical turning point. They will reflect back, but they'll also penetrate slightly into the wall. Now, it turns out that that's actually an observable phenomenon that people have used. It's used in what's called the scanning tunneling microscope. Have any of you heard of that or used one, maybe? Not? Because what you can imagine, let me say that let's make the wall high enough that the wave does not penetrate all the way through. or go over, it doesn't go over the wall, but it does penetrate part of the way. Now, if I made that wall thin enough, the wave would have some finite probability being on the other side. So they use this technique, and I'll demonstrate it more. I just want you to see it now, and we'll see it again later. They use this technique by saying, if I put a barrier here, I can still get some electrons passing through the barrier if it's thin enough. So what some folks did, they made a very sharp tip. They put a conducting surface here. They made a very sharp tip, and they brought so the electrons, this is a metal, and so its waves actually reach this barrier. They bounce off because they can't get out. It's like this tall barrier. The electrons don't have enough energy to get out, but they can leak out a little bit. They come out of the surface ever so slightly, and they brought this within that penetration distance, and they actually could get electrons to pass through the space between without actually having like an arc. It isn't like like a spark. It's actually the wave function of the electrons here